In this video we're going to look at some examples of multivariable optimization. Our first example is an unconstrained problem, and we're going to be looking for interior stationary points for the function shown here. The way we go about this is to start off by using first order conditions. We look for derivatives of partial derivatives of the function, and we set these equal to 0 in order to look for interior stationary points. So our first partial derivative, dz dx, is 2x plus 2 minus 4y, and we set that equal to 0. Then we take the partial derivative with respect to y, dz dy, that gives us 4y minus 4x, and that is also equal to 0. So we've got to look for a pair of values x and y which satisfy these equations. Now from the second equation we've got that y must be equal to x, and so if we substitute that back into the first equation we'll get 2x plus 2 minus 4x is equal to 0, and that allows us to solve for the value of x. So we'll get x is equal to 1, and because y is also equal to x we also have y equals 1. Now we need to determine the nature of the stationary point, and for that we use the second order conditions. We derive the second order derivative with respect to x, that gives us 2. The second order derivative with respect to y, and that will give us 4. Then we take the cross partial derivative, d squared z dx dy. Remember, it doesn't matter which way around we do this, and we get minus 4. Now we can show that this implies that this is a saddle point, because we have, if we take the square of the cross partial derivative, that's equal to 16. That's greater than the product of the second order partial derivatives with respect to y and with respect to x. So therefore we know that this point that we've identified is in fact a saddle point. Now the other type of problem we come across is a constrained optimization problem, and here we're going to look for values of x and y which minimize the function given here subject to a linear constraint. So how do we go about doing that? Well, our first stage is to set up the Lagrangian function. The Lagrangian function is given by our original objective function plus lambda, the Lagrange multiplier, multiplied by the constraint, where we express the constraint in this case as x plus y minus 1. Now this will give us three first order conditions, all of which we set equal to 0. So we set dl dx equals 4x plus lambda equals 0, dl dy will be equal to 2y plus lambda, and again we set that equal to 0, and then the third condition, dl d lambda, recovers the constraint for us. We get x plus y minus 1 equals 0. Now we solve that for values of x and y as follows. First of all, from the first two conditions we have minus lambda equals 4x equals 2y. This implies that y is equal to 2x. Now we can substitute that into the constraint, and this will give us values of x and y. So in this case we substitute this into the constraint and we get 3x minus 1 equals 0, which implies that x is equal to 1/3. And of course, since y equals 2x, we have y equals 2/3. And we can substitute that to get into the original z function to get the value of our objective function. We get z equals 2 multiplied by x squared, so that's 1/9, plus y squared, which is equal to 4/9. So z will be equal to 6/9, or 2/3. How do we know that this is a minimum rather than a maximum? Well, a shortcut here is to look at the contours of the objective function, and if we look at the contours of the objective function we see that they are in fact concave.